So, what is tensorization? So, tensorization, turning tokenized words into numbers that neural networks can process. So, computers and neural networks do not understand words directly like dog or love. Only process. They only process numbers. So, uh, it's pipeline like from the text convert to tokens, from the tokens into IDs, and from the token IDs converted to the tensors. So here's the big picture. Example the sentence I love my dog. um, Step 1, tokenization. So splitting those sentence um, into words. I mean splitting those sentence, like for example, the I is equivalent to 1, love is equivalent to 2. I mean, yeah, I love my dog. That's just tokenization, splitting the words. I mean, splitting the sentence. And next is vocabulary mapping, turning the word into IDs, like the value of I is 1, the value of love is 2, the value of my is 3, the value of dog is 4. Step 3 is tensorization, converting those IDs into tensor. This numeric structure can now be fed into models like RNS, LSTMs, or transformers. So, what is a tensor? A tensor is just a mathematical container for numbers. Think of it like dimensions, like having a one-dimensional tensor. This is a single sentence. One sequence of tokens IDs is 1, 2, 3, 4. The meaning is 1 is I, 2 is love, 3 is my, 4 is dog. Next is 2D or two-dimensional tensor. This is a batch of sentences, multiple sentences stuck together. Like we have the rows, each row is a sentence. For example, we have the row of having, like uh, this vector, like 1, 2, 3, 4, and there's another row also that contains the numbers. This is useful because models often process many sentences at once, like batch processing. Next is 3D tensor, more complex natural language processing structures. It is used when each word has multiple features or embeddings. Examples: having a batch size, sequence length, and embedding dimension. For example, the batch size is 32 sentences, sequence length is 20 words each, and embedding dimension is 768 features per word. This is common in BERT. Why tensorization matters? Without tensorization, neural network sees like sentence like I love my dog. The problem, model cannot complete language from raw words. So with tensorization, we have the values of 1, 2, 3, and 4. So the benefit um, now in PyTorch or TensorFlow can multiply matrices, learn patterns, and predict outcomes. So let's say we import the torques and we have the torque the tensor of 1, 2, 3, 4. And we print the sentence and its tensor output will become 1, 2, 3, 4. So the different ways to represent words numerically. First is one-hot encoding. What it does is this is one of the earliest methods. So we have the vocabulary I love my dog cat. If dog is the fourth word, then we will have value of 1 in that positions. Like if the dog is the fourth word, we will have 1 in the fourth place and the rest is 0. Why? Because only one position is hot, like 1. Everything else is 0. Example, I is the first, so the um, in in the list of numbers it will become 1 and the rest is 0 in the first place. Love is the second place, so it will become have 1 and the rest is 0. My is in the third place, so it will become 1 in the third place and the rest is 0. And the same as the dog and the cat in the fifth and in the fourth and fifth place. So the problem with one-hot encoding is, imagine vocabulary size is 50,000 words. So each word vector would have um, 50,000 words. That's problems. Huge memory waste, sparse vectors, no meaning relationships. Example, dog and cat are equally unrelated mathematically, even though semantically similar. Next is bag of words, OBOW. Instead of one word represent the whole sentence by word frequency. Like if we have the vocabularies, like I love my dog, cat. Sentence example, we have the sentence I love my dog. So the vector would um, like it slides up, it turning to one. And there is zero. Why? I appears once, love appears once, my appears once, dog appears once, and cat appears 0 times. That's why its vector position is become zero. The cat is zero. The rest is one because all of those is appears. Another sentence, my dog love dogs. Um, the third and fourth position becomes two because my appears 2 times and dog appears 2 times. In the sentence, my dog loves my dog. So the major limitations of a bag of words, it ignores word order. Uh, this I love my cat and my cat I love produce the same vector. The problem, meaning may differ but representation is identical. Next is TF-IDF or term frequency, inverse document frequency. This improves the bag of words or bow by reducing the weight of overly common words. For idea, words like I, the, my, is, it appears in almost every document, so they are less informative. So the formula is TF or term frequency is how often word appears in current document. And IDF or inverse document frequency, how rare word is across all documents. So TF subtracted by IDF, like for example, if dog appears often in one document but rarely elsewhere, so we could have high TF IDF. And if the word appears anywhere, so it become low TF IDF because um, it's so common, but the dog is not common, so it's we have the high score. So the benefits, it highlights important words. So the limitation, it still ignores word order, the context, it still ignores the context and the meaning. So why old methods struggle? One hot is huge vector, no semantic meaning, and the bag of words is frequency only, no order. And that term frequency and the inverse document frequency is better weighting, is still no context. So the modern solution is embeddings. Instead of giant sports vectors, word embedding, like for example the dog and the cat, um, their embedding numbers has semantically close, meaning they have closest numerical values in terms of um, vector values or embeddings values. So the dog and cat becomes mathematically close. Why embedding arcs for powerful? They capture semantic clarity. Like for example, dog approximate cat. King, man plus woman is when you combine those words, it's approximately close to the queen word. So here's a key concept to remember. Tensorization is a tokenization. Tokenization is a split text. Like if we have the sentence "I love my dog," it splits text into "I love my dog" and those who have vocabulary and having IDs. And tensorization on the other hand converts to numbers. Like if we have this tokenization "I love my dog" and then those turns into numbers, so the model could so it could be fed in the model and understand by the model. So the final pipeline is from the raw text, tokenization, vocabulary mapping, numerical IDs, tensorization, neural network. So yeah, tensorization is how language becomes machine readable math. So words is a human language, token IDs is barcode numbers, tensors organized spreadsheet of barcodes. The AI reads barcodes, not words. So most important takeaway: tokenization breaks text apart. Tensorization converts into tensors. Embeddings later make those tensors meaningful. That's a bridge from language to AI understanding.